Okay, so today we are going to discuss power flow equations. So first two classes we have discussed complex power and transmission capacity. Last class we have discussed bus admittance value, that is Y bus. Okay, and we discussed that by means of Y bus we are going to develop power flow solutions and solve it. Okay, so today's topic is how power flow equations are formulated. Okay, and next four classes will be discussing the solution of the power flow equation. So that will complete the load flow studies. And keep in mind that all these are part of one experiment in your power system lab 2. Code is already given to you. You need to explore. Whatever theory we are going to study here are algorithms that is implemented there. Also, you might have heard about that Mat Power software. Okay, it's just a zip file. You have to unzip it, put it in MATLAB workspace, and add to path. That's it. Okay, it's a very nice software. So all these methods can be implemented for larger. We will just manually solve only 2 bus system or maximum 3 bus. Okay. In that case, you have 5,000, 10,000 bus system. Okay. So we start with power flow equations. Okay. So before going to the power flow equations, what is our objective? In power flow equations, what is our objective? The objective is to compute the power flow. The objective is to compute the power flow between two lines, or in fact, I would say it is S12, the complex power, okay, which consists of P12 plus JQ12. Okay, that is our objective, and we have seen that we can compute this by means of the formula VI conjugate. Okay, VI conjugate, or V1 minus V2 into I conjugate. Okay, so the power flow problem. What is the power flow problem? So you can, in short, you can mention in your note. In the power flow problem, it consists of obtaining the magnitude and phase angle of voltages. Okay, so you find out V. Okay, then finally, eventually, you are going to calculate this P and Q, and in between I will be calculated based on the voltage and impedance. You know the impedance of the lines because that is specified. The impedance of the lines is specified. So using the impedance of the lines, you need to calculate the current, and then using the current, you need to calculate the power, compute the power, and that is our objective, to compute the power. Okay. In solving the power flow problem, the system is assumed to be operating under balance conditions, and hence a single phase model is used, which can be expanded or extrapolated to 3 phase. Okay. So this also you mentioned. This point number 1, what we need to get. Point number 2 is 4 quantities are associated with each bus. So each bus has following 4 quantities. First is the voltage. Suppose VSS UT voltage. Okay. So the bus. So we have a certain voltage level. So that is the voltage. The phase angle of the voltage, as I discussed with you, magnitude of the voltage is related to the reactive power flow, whereas angle of the voltage is related to the real power flow, actual power flow in the line. The real power P, the real power P, which will be injected, or which is the demand, and the reactive power Q. As we know, reactive power is never consumed, but then you need to transfer reactive power from one part of the power system to the other part, so as to maintain the voltage constant. Okay. And the very important point is that the power flow equations, as you will see, they can give you only the difference between the angles, not the actual angles. So delta I minus delta J means the voltage angle difference between 2 buses, which enables the power flow. That only they will give, not the individual angles. Okay, individual angles you can find out by taking a reference angle. Okay, we take a reference angle. All the generation variables cannot be specified a priori. A priori means at the beginning, before the computation, because losses are unknown. See, we say we need to transfer 200 megawatt of real power from Hirakud power plant to some bus. We know that. But then how much losses will occur in the transmission line, we do not know. Suppose while transmitting 200 megawatt power, you incur a loss of 2 megawatt. So your generating system should generate 202 megawatt instead of 200 megawatt, right? But we don't know that. It may be 2 megawatt, it may be 3 megawatt. So for that purpose, this is done in an iterative manner. First, the power load flow solution is solved. So suppose the load is 2 megawatt, then again it is solved. So 2-3 iterations, the losses are taken into consideration. Okay. Next one. A typical bus of the power system. This is taken from the Hadisada book. A typical bus of the power system. Draw this. Okay. Consider a typical bus of a power system network as shown in the figure. The transmission lines are represented by the equivalent pi models. You know pi models for medium transmission lines. Impedances has been converted into admittances as is the practice. For load flow we use admittances, not impedances, or to exploit the sparsity properties of the bypass matrix. Okay. So now the ith bus, the most general bus is the ith bus that we are considering, which can be a generator bus, load bus, is connected to various other buses through various lines like I1, I2 up to IN, and there is a ground connection also, the self admittance. Okay. So draw this. So how to find out the current that is flowing out from the bus? What is the equation? KCL equation? Vi minus V1 by into I. Vi minus V1 into Yi1. Vi minus V2 into Yi2. So all this summation is the total current that is coming out from the bus, and hence is equal to the injected current. Injected current may be because of a generator. Okay. Keep your mobiles in silent mode. Okay. So application of the KCL, it says the injected current is equal to YI0 V1 plus Vi minus V1 into YI1, Vi minus V2 into YI2, and so on. Right? That is, we have just seen that here according to this figure. Okay. So therefore, this can be written in this form. So as we discussed in the very first slide, the first objective is to compute the current. How to compute the current? We know the voltage. We multiply by the admittance. Where from we get the admittance? Where from we get the impedance? Where from we get the impedance? It's a line parameter. It's given in the chart. Okay, it's already available. It's a line parameter. Okay. So from the voltage, using the impedance, we compute the current. Okay. What is our objective? The objective is to compute the total power flow, which is Pi minus jQi equals to Vi into I conjugate. So write down these three equations here, right? First is computing the current from the voltage and admittance. Then computing the power using the complex power formula that we discussed in the very first class, Vi II conjugate. Okay. And why do we use this conjugate? As I told you earlier, why we need to use the conjugate? Follow the convention that inductors consume reactive power and hence Q must be positive, and capacitors generate reactive power and hence Q must be negative. Since inductors lag, the current in the inductors lag inductive load, not inductors, current in the inductive load lag the voltage by some angle, it is actually minus. But Q must be positive since it is consuming. So we use the conjugate. Okay. So the power flow equations are simply Vi into II conjugate. Now what is the current? This is the current. So II, this injected current is equal to injected current II is equal to Vi plus jQi divided by Vi conjugate. Okay. Here conjugate is taken. You see, it was plus here. We take conjugate of the both numerator Pi plus jQi, which is Pi minus jQi divided by V conjugate. So that is equal to this current value. And this is the power flow equation. This is the most general form of the power flow equations. So what are the steps? You have transmission line parameters with you, the impedance, convert that to admittance. Voltage is already specified, or compute the voltage for the unknown voltages. Then using this to compute the current. Once you know the current, use that to compute the power flow. Now this is at the core of the all algorithms that are implementing load flow. But then since the size is large, it is very clumsy or it is very time taking. Earlier it was done by hand in papers. 30-40 years back it was done by paper. Then some network models came. Okay, but after the digital computer arrival, it is done in computers. Okay. Next, so it is observed that, so what you observe, what is the power flow equation? It is observed that the mathematical formulation of the power flow problem results in a system of non-linear algebraic equations. These are algebraic, no differential. Why? Somebody answered that day that this is not a dynamic system. Time is constant. It's a snapshot of the system. So it's not dynamic. It's a static one. So, but why it is non-linear? When an equation is called non-linear? Where is the non-linearity in this equation? Anyone? It's a test of your promptness. What is the source of non-linearity? Linear one equal y equals to mx plus c. Okay, that is no. I'll give you a hint. When there is a square term, it is non-linear. But here there is no square term. Is it? Do we have a square term here? This is. There is one hint. If there is a square term, it is not here. But there is something else which is making it non-linear. What is that? Tell. It can be wrong. Just tell.
So different voltage lengths.
It is related to voltage. Linear means you have a number. Non-linear means either you have a square variable. Linear means a single variable. Either a square variable or some sine or cos term. And you will get it. Is there some sine or cos term here in this equation? Yes, of course. These are all vectors. This voltage is a vector. This y is also a vector. It is actually j some value or minus j some value. So these are all vectors. They have some angles. So this eventually results in some sine and cos. Okay, and hence the equation is non-linear. Okay. So since it is a non-linear equation and you do not have enough equations, so we use iterative techniques. Okay, we initially get some value, then iterate to eventually reach a value. Convergence. We converge. Okay, have you read numerical methods in your math? Newton-Raphson method, numerical methods. Okay, so we have to use numerical methods for solving this. Now next is the detail. That was the most general equation of the most general power flow equation. Now we are bothered about both real and reactive power. Now how to separate them out. Okay. So total power injected at the source is given by SI is equal to PI minus QI. Okay. Since it is coming to work with the current instead of the conjugate, so we take the conjugate of both sides. You know conjugate, what is the complex conjugate of P plus JQ? P minus JQ. That's the complex conjugate. So that is equal to simply take the conjugate of this side, which is VI conjugate into II. Okay. VI conjugate into, this is the current value. It's nothing. Simple summation of the voltage into admittance. Voltage into admittance or voltage by impedance. Simple. Okay. Now, as I told you, these voltages are what? Vector quantities. Okay. So any voltage can be written as a magnitude and an angle. In Euler form, it is Vk e to the power j delta k. Yik can be written in this way. Write down these two values of Vk and Y. See, these are both complex. Okay. This means cos delta k plus j sin delta k. Cos theta ik plus j sin theta ik. Now, if you substitute all this into this equation and separate the real and imaginary parts, we get the final real and reactive power flow equations as this. So here, what you do? Instead of Vk, you put this equation. For Yik, you put this. Okay? And then put the angle of Vi is delta I. See, Vi conjugate was there. Therefore, it is minus delta I. Since Vi conjugate was there, which is minus delta. Okay, write down these two equations. These are very important. Highlight them and put it in a box. In the exam, you might be asked, derive the power flow equations for a general case, for an n-bus system. In exam, there might be a 4-mark question. Derive the power flow equations for a n-bus system. Okay. So write down Pi and Qi. Done?
No, sir.
So what you can see here, the power flow equation contains Vi and Vk, two bus voltage magnitudes. The angle difference between them, delta K minus delta I, and the impedance angle theta Ik. Okay, impedance angle theta Ik. Now suppose it is a completely resistive line. What is the value of theta Ik? Sorry, it's a complete inductive line. We neglect resistance. In that case, what will be the value of theta? 90. So that means this becomes cos 90 plus this, which is cos 90 plus some angle is equal to minus sine that angle. Okay, so this should be converted into. So in many cases, approximate solutions are used where theta is taken as 90 degree, neglecting resistance. Okay, so don't get confused there. They simply take where from this 90 concept came. This is equal to what is admittance? Impedance is equal to R plus JX. Okay, what is admittance? Y, that is equal to conductance plus susceptance. Right? Impedance is equal to resistance plus inductance, whereas admittance is equal to conductance plus susceptance. So here in this case we have assumed susceptance. However, if we neglect this to be 0, this is 0 and this is infinite. So this becomes theta becomes 90. Okay. Now we come to what are the characteristics of the power flow equations. So what you observe. So there are, if you see there are n equations for P, n equations for Q. So there are 2 n equations, right? When you separate the real and reactive part, you get 2n number of equations. This part is asked in gate questions regularly. Okay. So there are n real and n reactive powerful equations, giving a total of 2n powerful equations. Now there are 4 variables at each bus, right? We told voltage magnitude, the angle, Pi and Qi. So total of 4n variables. So you have a 4n variables but 2n equations. How to solve it? Anyone? Come back. You know that simultaneous linear equations. Suppose there are 3 equations, 3 variables, you need 3 equations. Suppose there are 4n variables, you need 4n equations. But we have only 2n equations. Then what is the solution? What is the way forward? To?
We can get the next 2 by solving that 2 solutions.
Okay, he gave one answer. Any more ideas? How to solve 4n variables from only 2n equations? Suppose you go to the exam and there is no negative marking. Okay. So you know the answer of 2. Remaining 2 you don't know. What you do? Yes. So just like that, we will guess 2n values. We will assume. So out of 4n variables, we will assume 2n variables. And remaining 2n variables we will compute. Then iterate. Now what to assume? Now the question is which one to assume? We have got voltage angle, we have got voltage magnitude, P and Q. Which one to assume? That is the question. And at what bus? At what bus, what to assume? Okay. But eventual solution is always we have to compute the voltage values. Okay. We have to compute the voltage value. So either you can assume V magnitude or angle. Right? Or both. We'll see that. Okay. So if at every bus two variables are specified, that means total 12 number of variables, thus specifying total of 12 variables, the remaining two variables are empty ones can be found solving 2n power 2 equations. So next is, when a physical system is considered, specifying variables of each bus depends on what devices are connected. Is it a generator bus? Is it a load bus? Okay. So we have this, you mentioned, write down. So we have four kinds of buses depending on which variables we specify. So one bus is slack bus, or this is the largest generator generally, where both the voltage, magnitude and angle is specified. Generally 1 0, 1 per unit, 0 angle. Unknown is P1 Q1. Okay, that is mostly the losses in the system. Okay. PQ bus, known is the load demand. You need to find out the voltage, magnitude and angle. Okay. Again, this is another repeated. Okay, this is for a particular 4 bus system, that's why it is repeated. This is an example where we have a 4 bus system. Two are, this from the Elgart book, 2 are load buses, one is a reference bus, and one is known as generator bus or PV bus. PV bus means it is a voltage bus. Okay, so you know the magnitude of the voltage. So in this case, you know the real power because the generator is generating real power, and you also know the voltage magnitude. Okay, this will be asked for sure as a 2-mark question in your exam. Okay, so remember it. PV bus, the magnitude of real power and voltage magnitude specified. You need to know the reactive power. Okay, you need to compute the reactive power. Okay, so summarizing bus classification. So what is the, we'll summarize now what we discussed. The system buses are generally classified into 3 types. System buses are generally classified into 3 types. One is slack bus or the swing bus. It is known as the slack bus. It is taken as reference where the magnitude and phase angle of the voltages are specified. This bus makes up for the difference between the scheduled load and the generated power. I just told you, at the beginning of the iteration you do not know what will be the loss. So whom to assign that loss? To the reference generator, okay, or the slack generator. Then load buses. These are the, suppose there is a power system, 90% buses are the load buses. Okay, generator buses are very less because every bus where the power is consumed is a load bus. Okay, so you have here active and reactive power specified, magnitude and phase angle of the bus voltages are unknown. Okay, then the one which provides the power to the system, those are known as PV buses. So real power and voltage magnitudes are specified, phase angle of the voltage and reactive power are to be determined. Okay. Now the question is, suppose there is a PV rooftop. Which kind of bus is a PV rooftop system? Or load? Because our home is there. What kind of bus? PV bus. Suppose I have a rooftop PV on my home. So is it a load bus or a PV bus? First thing is I don't specify the voltage. Okay. The homeowner is not going to specify his voltage, fix his voltage. It is the system voltage that fixes it. Mostly the rooftop PV buses are load buses. Okay. They generate some real power. Okay. So it is a kind of grey area. It's a new research. What kind of buses you should classify? They are generally part of the distribution system under load buses. Even wind generators are sometimes considered as load buses, at least for Q. Okay. Here we are considering only the conventional power system with centralized generation. Okay. Next, now when you see a power system, so we have to distinguish some variables, okay, known as disturbance variables, which are not under our control. The power system never knows how much demand will be there, theoretically, but actually it knows. The operators, they know what will be the next demand. Suppose at 12 p.m. today, what will be the estimated demand? They know. How they know that? Forecasting. Very good. So by forecasting the load based on the past data. Okay. So that is known as the uncontrolled variable. Okay, not under the control of the system operator. It is at the consumer level. But then, since you are studying smart power grid also, advanced metering infrastructure you will study. By using special metering techniques, you can control the load behavior of the consumer. So you can change the pricing, right? Suppose during 9 to 10, suppose 10 years down the line, EVA completely penetrates into the system. Now everybody will charge their EV. So the power supplier says, okay, from night 12 to morning 6, the power cost is only 3 rupees. From 9 am to 5 pm, it is 10 rupees. So everybody will charge their EV in the night only. So you are actually dictating the load, and that is what is known as smart grid. In smart grid, you have a module, right? AMI. Syllabus, have you not seen? Okay, that is the complete module on one of the major component of smart grid is advanced metering. Okay, smart metering. Okay. Okay. The control variable. Okay. So in under control variables, we have two kinds. One is the state variables. One is the control vector. Okay, you are going to study all this in your control 2 when you will study about state space. Okay, state space models and controllability and observability. In your control system you are going to study. So these are the variables that are the control variables. Okay, control variables means that we change in the system. We can change the generation of a generator depending on the demand. Okay, just like I told you, as he rightly said, we forecast the load. So we forecast it to be 230 megawatt. So the OPDCL or the hour is, what is that called? Odisha State Load Dispatch Center, SLDC. Okay, SLDC estimates that it will be 300 megawatt at a particular time. Now suppose it becomes 302 megawatt. What will be done? Nothing. You will just simply minor changes in the generator. Okay, mostly the fast generators they will provide, or spinning reserves. Okay. State variable is how we know the state of the system. What is the voltage? If the voltage is less, okay, that means there is a reactive power shortage at a particular system. Okay, voltage angles that you can measure so that we can know. We have got in smart grids, also it is there in your smart grid module, synchroscopes, not synchroscopes, sorry. What is that called? Have somebody says? That measures all these angles, voltage, magnitude and angles throughout the system. Okay, for real-time operation in a smart grid. And I just forgot. Okay, there is a device. Okay, not synchroscope. Synchroscope is for synchronization. Okay. Okay, there is some device which measures voltage. It is now embedded throughout the country. Okay, which is enabling this smart grid operation. It's kind of a real-time control of the power system. Okay, it is mentioned in your syllabus. Module 3, I think. Smart grid module. PME. Yes, very good. It is known as phasor measurement units. Okay, which measures the phase angles of the voltage. Because as we know, it is only the phase angles that dictate the power flow, not the voltage magnitudes. Okay, phase angles are a system-wide phenomenon. Voltage magnitudes are local phenomena in a power system. Okay. Next. So this is the complete formulation of the load flow problem. Okay. Assume a certain nominal bus load configuration. Specify PG and QG at all PQ buses. It is PD. Okay. PD. Thus specifying the 2L variables. Okay. It's not PG, it is PD. Load buses are where, how can there be generation? Okay. So at all load buses or PI and QI you can say. Okay. Then at the generator buses, at the slack bus we specify this is generally 1 0. Okay. It is always 1 0. 1 per unit, 0 angle. Okay. Then we solve the load flow equations. Now there are a minor modification in the algorithm if these are PV buses or PQ buses. Okay, PQ buses both are known, whereas in PV buses the Q needs to be found out. Okay, or Q needs to be specified. Okay, so here is given in case 1 what are the known variables, what we need to find. In case 2, okay, when both PV and PQ buses are there, so in that case, in what buses we have to find out. Okay, these are given for PV buses. These are given for PV buses, and for PV buses we need to find out this. Two different kinds of buses. Every algorithm has this option of distinguishing between PV and PQ buses. In MatPower, if you have downloaded, go to the data folder. In that you will find the case files where all these things are specified. And finally, this is one question for your exam. It is from the elder book. Okay. Find out the load flow equations for this two-bus system. Okay. Generalized load flow equations. Draw this two-bus system. Draw the two-bus system. How to find out the load flow equations? As we have seen in that general case. So you know S1. S1 by V1 is equal to I1 conjugate, right? V1 into I1 conjugate is equal to S1. V2 into I2 conjugate is equal to S2. Right? Now what is I? I is equal to two parts. One is going to this, in this direction to the ground. One is going in this direction. Okay? V1 into Yp, V1 into Ys. But then we are using Y bus, which is a combination of these two. The diagonal elements are simply minus Ys. Sorry, the diagonal elements are Ys plus Yp, whereas the off diagonal elements are simply minus of this impedance, admittance. Okay. So now we'll see how. This is only a simplified version of the first one. Only draw the first part. Okay. Okay. So this is how we write the load flow equations. So I1 is equal to S1 conjugate divided by V1 conjugate. So we get this in terms of C. We are using Y bus matrix so as to generalize it. Now you write down all these four equations. See, this derivation will be asked in your exam. Okay. Fine. So we'll stop here.